Hello, and welcome to video 2 from section 4.2. This is on the column space. So the definition, the column space of an m by n matrix call A is the set of all linear combinations of its columns. So if A is the matrix whose column vectors are A1, A2 up through AN, then the column space of A is just the span of those column vectors. Okay, and the first quick theorem we get is that the column space of an m by n matrix is a subspace of Rm. And the proof is really quick. We saw a theorem last section that any span of vectors is a subspace, and so this is a span, so it's a subspace. So by theorem 4.1, yeah, any span is a subspace. So yeah, column space of A is a subspace. Boom, sorted. Okay, and as always, let's go over an example to make this more concrete. Oh, there were a couple of notes first. The space there is for a reason. Yeah, so then note another way of writing the column space of A is saying it's the set of all vectors B with the property that B is equal to AX for some X in Rn. Okay. Let's give ourselves some space actually. Oh, move that whole thing down. Boom, there we go. There's our proof. There's a little note about how another way of writing down what the column space is equal to. Okay, now we get to this example. Let's let A be this matrix and let B be the vector 1, 4, 0. We want to determine if B is in the column space of A. So we want to determine if B is a linear combination of the column vectors of A. So our solution is, yeah, we want to know. So we want to know if AX is equal to B is consistent. So we're going to row reduce the augmented matrix. Yeah, we need to row reduce. Row reduce the augmented matrix. So we'll start with 1, 0, negative 1, 2, 1, 3, 3, 1, 2, 0, negative 1, 1, 1, 4, 0. So like I said before, it may sound like we're introducing new notation, and we are, but the actual like mechanics of what we're doing is not much different than what we're doing in section 1, basically, or in chapter 1 at least. Still row reducing matrices. Okay, so let's do R3 plus R1. So the first two rows aren't going anywhere. Sorry, that one needs to move over. Oh. Yeah, 0, 5, 5, 1, 1. And then what? Let's do row 3 minus 5, row 2. Oops, it's too long. 1, 2, 3, no, 1, 0, 1, 1, negative 1, 4. And yeah, 0, 0, 0, 6, negative 19. Okay, and we are, yeah, let's scale row 3. 1, 2, 3, 0, 1, 0, 1, 1, negative 1, 4, 0, 0, 0, 1, negative 19 over 6. And yeah, now we're in, or not quite. We'll use this one to kill off everything above here. Then we'll be all set. Or almost all set. Yeah, we've got a couple moves left still. All right, let's see what we want. row 2 plus row 3 will do it. Let's do row 1 minus 2 row 3. Sorry. Something must be written down wrong. Let's do this one and see what happens. Certainly we want row 2 plus row 3. 1, 2, 3, 0, 1, 0, 1, 1, 0, and then we've got 4 minus 19 over 6. We'll worry with that. We'll worry about that in a second. And then row 3 hasn't changed. 0, 0, 0, 1, negative 19 over 6. And what's left is to, yeah, take out that 0 in row 1, column 2. So let's do row 1 minus 2 row 2. So now 1, 2 minus 2 is 0, 3 minus 2 is 1, 0, and now we've got to do, okay, 1 minus twice 4 minus 19 over 6. Okay, forgive me for not doing that in my head. I've got a lot of skills, but mental arithmetic, just not one of them. Okay, but I mean, the important thing is we've got a consistent system. So we get a, yeah, since the system is consistent, the equation AX is equal to B can be solved. And in fact, as soon as we sort out what 4 minus 19 over 6 is, then we'll have a solution. But that is, we weren't asked to find a solution, just asked to see if B is in the column space. And so we can conclude, so yeah, B is in the column space of A. Okay. I guess that's the column space. Tune in next time for linear transformations. Take care, everybody.